How do we translate a multiple quantified statements? For example, remember the definition of reciprocal. Reciprocal of a real number like A is a real number like B such that A times B is equal to 1. The following two statements are true. Every non-zero real number has a reciprocal. This is true all the time. We learned it in algebra. So we can write it every non-zero for any non-zero real number. There exists, it has a reciprocal, there exists a real number like B such that it satisfies the reciprocal relation. The next statement is there is a real number with no reciprocal, which is 0. So there exists, you have existential quantifier, you have a number like C such that with no reciprocal, it means that it doesn't matter what number you're going to select, it doesn't satisfy the reciprocal formula. Let's take a look at only if example. Rewrite the following as a universal condition statement. A product of two numbers is 0 only if one of the numbers is 0. You can write it this way. If neither of two numbers is 0, then you can conclude that the product of the numbers is not 0. Or you can basically use the contrapositive. If a product of two numbers is 0, then one of the numbers is 0. Very well. Consider two sets D and E to be equal to each other, and they are including -2, -1, 0, 1, and 2. Write the negation for each of the following statements and check to see which one is true, which one is false. It says for any x in domain D, we can find a y such that x plus y is equal to 1. Its negation, the negation or for all, is there exist. The negation of existential is universal, and the negation of the statement itself. So it says there is an x in D such that no matter what you choose for y, x plus y is never 1. The negation is a true statement. Why is that? I can find one x value, which is -2 in this set, that the only number y satisfies this relation is going to be 3, which is not part of this set. So the negation is true. Since the negation is true, we can easily say that, hey, the original statement is a false statement. B, there is an x in D such that for any y in E, x plus y must be equals to -y. Its negation, the negation of existential is universal. For any x in D, here, the negation of universal is existential such that, and you're going to negate the predicate, which can be written as x plus y, which is not equals to -y. In this case also, the negation is a true statement. For any x in D, you can find a y such that x plus y is not equal to -y. So this statement is true. You can show that this statement, the original statement, is false. To see the original statement to be false, you can take any x in domain D and choose y to be any number in E. When y is not equals to -x/2, then this statement becomes a false statement. Since 2y is not equals to -x, and adding x and subtracting y from both sides gives you x plus y, which is not -y. It's just simple algebra. Let's move on to more examples about these two sets. Consider the following case. For any x in D, you can find a y such that x times y is more than equals to y. The negation of universal statement is existential statement. The negation of existential statement is universal statement. And the negation of xy more than equals to y becomes xy less than y. So the negation is for there is an x in D such that for any y in E, xy is less than y. The original statement is a true statement, so its negation becomes false. Let's take a look at the following table showing all possible choices for x that could match with a y so that xy more than equals to y is a true statement. So you have 5 options for your x. What is the value for your y that satisfies this relation? If you take x to be -2, you can take y to be -2, and -2 times -2 is 4, which is more than equals to -2. So we're good for the first choice. If x is equal to -1, you could take y to be 0. 0 is more than equals to -1, which is true. Make xy more than equals to y a true statement. If you take x0, y1, then 0 is more than equals to 0. The next option for x is 1. Y can be 1. 1 is more than equals to 1. And finally, if x is equal to 2, your y can be 2. 2 times 2, which is 4, more than equals to 2. Next statement, there is an x in D such that for any y in E, x is less than equals to y. Its negation, for any x in D, you can find y in E such that the negation of x is less than equals to 1, which is x is more than y. The statement is true. There is an x in D such that for any y in E, x is less than equals to y. In fact, -2 in D is the smallest x in set D, such that if you take any other y, -2 is less than equals to that y. So since the original statement is a true statement, the negation becomes false. In this example, for any real number like x, we can find a real number like y such that x plus y is equal to 0. Given any real number like x, we can find a real number like y so that the sum of the two is 0. In other words, every real number has an additive inverse. Basically, this statement is true all the time. What if I write it this way? There is a real number like y such that for any real number like x, x plus y is equal to 0. So you should be careful about the order that you write the quantifiers. Take a look. This guy says there is a real number with the following property. No matter what real number is added to that number, the sum of the two will be 0. In other words, there is one particular real number whose sum with any real number is always 0. This statement is false. You cannot find one real number that works for this statement. If x plus 0 is equal to 0, then x must be 0. But what if you have x plus 1, which is equal to 1? This is not equal to 0. So again, the order of quantifiers is super important because sometimes you should be careful you get a wrong or false statement. The meaning of the statement will change if you change these orders.